Hello my dear friends, welcome back to our YouTube channel. This is your ADC Max. What are the boundary conditions? What are the boundary conditions for the one-dimensional heat flow equation? Yeah, first of all, what is one-dimensional heat flow equation? Dou U by dou T is equal to alpha square into dou square U by dou X square. What is alpha square? Alpha square is the diffusivity of the substance, that is K is equal to rho, that is alpha square is equal to K by rho into C. Rho is the density, C is the specific heat, K is the thermal conductivity. Right? Now if I solve this by using the method of separation at variable techniques, please kindly see my video, go and watch my video. That is, I have did the separate video how to solve by using the method of separation at variable techniques to get the all possible solutions of one-dimensional heat flow equation. So among the three possible solutions, this is the correct solution: A cos Px plus B sin Px e power minus alpha squared P squared T. Got it? Now let us look into this equation. I found that U can be differentiated with respect to x twice the time, 2 times, right? So there are probably two unknown constants for x alone. So there are two unknowns in the system of equations. We need at least two distinct boundary conditions. So two equations, two conditions, two constants. Why? Because of the degree is 2. What about U? U with respect to T only 1 time. So there may be only one condition for the time factor T. Yes, absolutely, you are correct. So there are three boundary conditions for the one-dimensional heat flow equation. So what are the equations? If we consider a bar or maybe a rod, of length L, let us heat this material by using the first empirical law. Is called heat flows from higher to lower temperature. So once we heat it, it will be transformed to the entire rod or bar, but this can be insulated laterally, the entire surface. So let us measure the temperature only at these two endpoints, left end and the right end. At the left end, when x equal to 0, the temperature is assumed that 0, or sometimes it is non-zero. If the right end at x equal to L, what will be the temperature? The temperature is 0 sometimes, what happen? Non-zero will happen. So during this heat conduction, if I fix a point in the rod, can I measure the temperature distribution? How the temperature was distributed throughout the bar. So that is my aim. Our aim is to find out the temperature distribution function of the given heat conducting material. Let us see that how to write the boundary conditions. Very simple concept. As I told you that there are two conditions for the x and only one for the t. That means that is initially. At the time initially means time t equal to 0. So the first boundary condition is when x is equal to 0 for any time t, then 0 temperature for all the time t is equal to 0. And the second boundary condition for when x is equal to L, the right end x is equal to L, the temperature is maintained as 0 for all the time t is equal to 0. And third one is for t variable. So what is the initial temperature distribution of the rod? What is the initial temperature distribution of the rod? It may be given in the problem. Otherwise, we have to calculate or estimate or determine the initial temperature distribution from the given idea. So when t equal to 0, the temperature is given. Sometimes it may not given. That time you have to find out that value. So these are the three boundary conditions for the one-dimensional heat flow equation. First boundary condition for x equal to 0, second one for x equal to L, third one for time t equal to 0. Suppose initial temperature distribution is not given, what we can do? Let us find out that too with help of the steady state. So when we say that the state is steady state, when we say that the state is steady state, tell me, that means that the temperature is fixed. The temperature is constant. The temperature is constant or will be fixed. Once it will reach its boiling point, it may reach the maximum temperature. So when we say that the state is steady state. Once a state in which the temperature does not vary with respect to the time t. The temperature does not vary with respect to time t is known as the steady state. So what is the use of this steady state? Yeah, absolutely. We can apply this steady state conditions. We may get the third boundary condition. Sometimes it is not given to you directly. So we have to estimate the initial temperature distribution by using this steady state concept. Now once again coming back to the one-dimensional heat flow equation. What is one-dimensional heat flow equation? The one-dimensional heat flow equation is dou u by dou t is equal to alpha square into dou square u by dou x square. So under steady state what happened? Under steady state, what is steady state says that the temperature does not vary with respect to time t. The temperature does not vary with respect to time. Means once it reaches the maximum point of the temperature, then it will be stable. It cannot be raised then thereafter. For example, let's consider the boiling point of the water. What is the boiling point of the water? 100 degrees Celsius. Once it reaches the 100 degrees Celsius, later on, even though when you heated the water, it will be boiled only. It cannot be raised its temperature. It's not possible. So that state is called the steady state. So the temperature does not vary with respect to time t. That means that the temperature is fixed. It's a constant that time. So once the temperature is fixed at that time, then that constant becomes 0. So what's the rate of change of the temperature with respect to time t? It is equal to 0. So under the steady state, dou u by dou t becomes 0. So 0 is equal to alpha square. Not only that, once it is under the steady state, the temperature does not vary with respect to time t. That means that u is a function of x comma t becomes u is a function of x alone, because temperature does not affect the time factor. The temperature does not change with respect to time t. That means that the time factor does not affect the u. So u becomes a function of x alone. So this becomes ordinary differential equations. This is having more than one parameter, is a more than one variable, then this comes under partial. Once under the steady state, the temperature does not vary with respect to time t, so it becomes the only function of only one variable. So this becomes the ordinary differential equation d squared u by dx square. Now the product of these two equal to 0. Obviously alpha square is the non-zero value because it is the diffusivity of the substance. K by rho into C. K is the thermal conductivity, rho is the density, C is the specific heat. Everything is non-zero. So once this is not equal to 0, then which one is 0? D squared u by dx squared equal to 0. So let us solve this equation. You will get. So for the first time, I can go for the two methods. The first method, can I take this as the equation? We get m squared equal to 0, which means that m equal to 0, 0. The roots are same. The roots are equal. Real and equal, 0 and equal. So what's the complementary function? Or the u under the steady state, u of x comma 0 is equal to a x plus b into e to the power 0x. What's e power 0? 1. Otherwise it is simply called ax plus b. This is called the initial temperature distribution until the steady state conditions prevails. It's often called as steady state solution. Is often called as steady state solution, is also known as initial temperature distribution until the steady state conditions prevails. So this is the way to get the steady state solution or the third boundary condition. Okay, sir. On the other hand, we can solve this by first time with respect to x. So let us integrate this with respect to x. I get the constant a. Integrate with respect to x first time. Again, let us integrate with respect to x second time. So on both these sides we get integral a becomes integral ax plus b. The left hand side differentiating with respect to x and the integrating with respect to x will cancel. So let us do integrating this with respect to x 2 times. First time we get the constant a, second time one more time we get ax plus b. So this is also the solution by direct integration method, otherwise by using the complementary function and the particular integral case. Particular integral doesn't matter because the right hand side is 0, so there is no particular integral. And the complementary function from the left hand side, we may get the m squared equal to 0 or m equal to 0, 0. The complementary function is ax plus b into e to the power mx generally. Here m equal to 0, so 0 is equal to 0 is 1. So ax plus b only is the complete solution. It is often called as steady state solution. It is also known as the initial temperature distribution of the given one-dimensional heat flow equation. Thank you so much for watching our YouTube channel. Please kindly subscribe and share, comment, like your YouTube channel ADC Max. Thank you so much.